So wind power is what I'm realizing myself is it is growing tremendously. So why are we talking about wind? Well, in 2017, it was America's second largest renewable energy source. It makes up 21% of the total renewable energy portfolio. It's present in 40 states. It is clean energy, and it's adjustable based on demand. Well, I'm going to go into this demand and the adjustable part of the grid's demand here later on in this presentation. So over on the right, this is actually the most up-to-date graph I could find, which was very surprising to me, but that's what it is. So you can see different options there. So what is wind energy? Well, if you look over here on the left, you can see basically the process of how it's going to work. But wind energy is a process by which the wind is used to generate mechanical power or electricity. Turbines convert kinetic energy to mechanical power. And in physics, kinetic energy of an object is the energy it possesses due to its motion, work needed to accelerate the body of a given mass from rest to a state of velocity. Now, we're going to get a lot simpler after this, but this is the fundamentals on how it's going to work. And yes, I did steal these pictures from somebody else. So wind to electricity, the opportunities in this field are that 36%. So 36% of the wind that's available in the sphere of the turbine, they're able to collect. So technically a wind turbine, a commercial wind turbine, is only 36% efficient. Now, reading this morning on some updates, they're starting to get up around 50%. They haven't been able to prove that yet, but some of the bigger units are pushing 50% according to the engineers. So it is renewable and abundant. It's adjustable per demand. It's cost effective. It has a low operating cost. Basically, you set it and forget it. And it has a small footprint. The challenges are, even though it's cost effective, it's still very expensive up front. Oftentimes they're located out in agricultural territory rather than being close to cities where a lot of that energy is being used. There is noise and aesthetic pollution, and it has an impact on local wildlife, killing birds and bats. So it affects bats move around in packs, and it kind of changes how they move around in our airspace. So turbine basics, you've got the rotor, which the blades are attached to, and that rotor is also attached to the generator. You see the tower, you got the foundation, and the nacelle, which is where all the components are, the generator, the housing. And some of these generators, you can climb down into this. They're large enough to access, and I'll show some pictures of that here in a minute. So wind turbines provide mechanical energy. They are used for grain. They're used for electricity production. They're used for pumping water. And a lot of times over history, they've been used for many other things as well. So wind turbines have two different types. You've got a horizontal axis wind turbine, which the turbine is horizontal or parallel with the ground. And that's typically used in wind farms. The vertical axis wind turbine is a rotating axis that stands vertical or perpendicular to the ground. These are for smaller projects and residential applications. So typically, if the land is not as opened up as it is out in an agricultural area, you've got more housing and maybe trees around, they like to go with a vertical axis turbine. So the benefits of the horizontal axis turbine is it's got low torque ripple, It's highly reliable. Most common is 3 blades. Wind energy converter wind farms are becoming an increasingly important source of intermittent renewable energy. So, and I'll touch on the intermittent part in greater detail whenever I'm discussing demand as well. So the vertical axis units are often used for rooftops and ship applications, and the straight vertical blade sections that are attached to the central tower with horizontal supports. So that's the dry row mill. It's got the horizontal supports on it. And you can see a picture of the two here. Here's the difference. You've got on the left, you've got the horizontal axis, and on the right is the vertical axis. So here's the components, the internal working components of the unit. So you've got the rotor and the turbine and the generator, all located right there in one spot. So the air flows turning the blades turn the shaft turns the gearbox. That gearbox basically increases or decreases. In this case, with a windmill, it's going to increase the rotation that turns the generator, creating the magnetic field, creating the electricity. So the rotator is the key in this. So you can see all the different components there. These are all put together out in the field. Many people have seen them traveling down the road. One of the blades typically is the length of a semi-trailer. So they're quite large, 70 feet, give or take. Here in Rockville, we had a bunch of them come through years ago. A lot of those were in the ballpark of 70 feet long. So this is what a magnetic field looks like. They say there are certain imagers that can capture this. I've never seen one, but Michael Faraday discovered that moving a magnet inside a coil of wire would create electricity. A turbine generator is the mechanism that converts the kinetic energy of a moving fluid to mechanical energy. So this is the conversion right there. Here's a list. If you watch the hydro presentation here in a few weeks, you'll see this slide right here as well. This is going down through the list on efficiencies. So you see your wind turbine down here about the middle. It's pushing mid to upper 30 percentile on this graph. And when you compare that to a coal-fired plant, it's less efficient than a coal-fired plant. That was kind of surprising to me. I thought for sure it'd be more efficient. However, cost-benefit ratio is much better with a wind turbine. This is across the United States. This is where a lot of these wind farms are located. You can see you've got some altitude there in Colorado where there's a conglomerate. But then you get over here by the Great Lakes and you can see how the jet stream, what you see in the upper right corner of this is the jet stream for the summer pattern, and the winter pattern is lower. So these patterns move down in the wintertime. So what you see is the jet stream, the lower jet stream passes through mid Indiana in the summertime, and then the upper jet stream, I couldn't find a good graph on that, but the wintertime jet stream is also mid-state Indiana. So right through the Midwest, that jet stream is coming through there, and you can see the placement right there in Wisconsin, Illinois, Indiana, Michigan, and even some in Ohio. They're capturing as much as they can with the jet stream. The jet stream moves south and at a lower altitude and right here around the Great Lakes. So it kind of creates a unique situation around the country. So here are some of the Indiana wind projects. The Fowler Ridge Wind Farm, which is in Fowler, Indiana. It's located also in Benton County. A lot of people around here refer to it as the Benton County Wind Farm. They broke ground in 2008. It was developed by Orion Energy and Vision Energy, and it has a nameplate capacity of 600 megawatts. Now, 2018 annual generation was 1.4 million megawatt hours of energy. So the 600 megawatts, the nameplate capacity, 600 megawatts, is what it can produce per hour at maximum capacity. The 1.4 million annual megawatts is what it produced over time, the annual megawatts per hour. So that's what it produced over a 365-day time span. So that's how you get the difference there. This is quite impressive. Driving up 63, we go to Chicago every now and then. You can see these windmills. They look like they go on forever. It's very, very neat. Also up there, this is in Benton County as well. I've always thought they were one site, but they're two different sites that commingle. You've got the Goodland Wind Farm. It's in Earl Park, Indiana, also in Benton County. They broke ground in 2003. It was also developed by Orion Energy. This site has a nameplate capacity of 130 megawatts. I could not locate a annual megawatt hour output on that, but I'd imagine it's about 1/5 the amount that the Fowler project is. So still quite a large project. These are major producers even in the local grid. And we'll get to the grid here coming up. So this is, when people talk about the grid, you just think more locally. Well, MISO, which is the Mid-Continent Independent System Operator for our area, covers all of Indiana, almost 100% of Illinois. And you can see how this area, the highlighted area, the green, the blue, some of the orange, this area is managed by MISO. There's a lot of reasons for that. This company was brought into place in 2001. And one of the main reasons this was created was due to Enron and the Enron scandal. There's a whole big mess with that and a long story, but this MISO was created to be an independent operator of generation sites and the transmission sites, and they have control over the wind, hydro, all this stuff in this geographical area. And all these generation sites, the coal plants, the nuclear plants, they're all a contributor to this interconnected grid. So MISO, it's an independent, not-for-profit organization that delivers safe, cost-effective electric power across 15 U.S. states and the Canadian province of Manitoba. It's a very large area, almost the central part of North America altogether. MISO exists to provide an independent platform for efficient regional energy markets. Since 2001, we have fostered wholesale electric competition in the region, creating greater system reliability and established coordinated value-based regional planning. This was actually a real-time snapshot from MISO's website, and it's showing me the load on these hubs. So the load on the Illinois hub right here, you see it's 51.64 megawatts right there. And also the Indiana hub, about the same, 51.05 meg worth of energy. And that's real time. That's what's going through those management groups right there. So there's a group here in Indiana, Indianapolis, Indiana. This place, I've been to this place. It has armed guards on in the entryways and standing on the rooftops of the buildings. Armed guards are around this all the time. It takes a lot to even get in there for a tour, and it's just a very unique building. It's also built for a Category 4 tornado, direct hit from Category 4. So just a pretty unique thing, something that I did not know even existed until I started working in the industry. You can see also by looking at this Michigan hub, this orange area up here where it's really hot in the top right corner, they're at 85.16 meg. That is, that's a system that's peaking. They're reaching their peak. They're hitting their high demand in that area. So this is a real-time snapshot also of the fuel mix. This was at 3 p.m. yesterday afternoon. The conditions yesterday were 88 degrees Fahrenheit, which is pretty warm. And we had quite a bit of sun. So it was partly cloudy, but we still had quite a bit of sun. If we look at this again is for this entire area. So our area may have been partly cloudy. Much of that area was full sun. So in this real-time snapshot, you can see the wind, which is the green slice here, wind contribution at about 3 o'clock yesterday afternoon, which is 2:25 really, if you look at the Eastern Standard Time there, was 1,065 megawatts worth of energy. This is yesterday. Now, there wasn't very much wind yesterday here at the surface of the earth, but you get up north in Benton County where the jet stream comes down a little bit low on the continent and low in altitude, you get a lot more wind there. So that portfolio at that time was 99 megawatt, 99,000 megawatts of energy, and wind was a little over 1,000 of that contribution. Again, this is real-time data yesterday taken off of their website. So I wanted to get a comparison. So fuel mix at 8 a.m. this morning, which is quite a different scenario. Our area was 74 degrees, full cloud cover. So wind, of course, we've got some storms moving through the area, and wind is capturing as much of that as they can. So our wind was 5,314 megawatts of energy, which is a bigger slice percentage-wise of the contribution at 8 a.m. this morning. The total megawatts was 68,000, and wind, again, very big percentage of that in real time. So wind is kind of a funny, wind and hydro are something that these operators with MISO can start and stop. So if I can get into the weeds a little bit, and if there's questions that come out of this, please ask it. But whenever you fire up a coal site, it takes a couple days to get it up and running, and it takes a couple days to bring it down, to shut it off. And it's a tremendous amount of work. You typically only do that in spring and fall. So once they get it running, it just runs all the time. And that's what's called a base load contributor to the grid. So you might be getting, say, 1,000 megawatts out of a site, a coal site. They're going to run that all the time. They're not going to call as an example this morning, MISO is not going to call that plant and say, hey, shut it down. Go ahead and shut your plant down. We don't need it this morning. We might need it tonight, this afternoon, or maybe even tomorrow morning, but go ahead and shut it down right now. Once they shut that down, they can't bring it back on. But these operators do have the ability to shut down large chunks of wind. So they can put the brakes on some of this wind. That's why at times you'll drive up through these areas and you see some windmills are moving, some windmills are not moving. And that's all based on what the grid requires at that time. So by applying those brakes, they're able to prolong maintenance on that based on run hours and extend its life expectancy. Also, if they don't put the brakes on it and go ahead and let those windmills spin and produce energy in excess of what the grid needs, we don't have a viable way of storing it. So if they produce too much, it's just gone. There is no way to capture that and store it and use it later on. There is, but not cost effectively at this time. So if they overproduce, it has no impact on the economics of electricity production. So same with hydro. Hydro is better. Hydro can store. So you can store energy with hydroelectric dams. So you can, during a higher demand time, which is typically in the Midwest, is typically between 4 and 6 p.m. So these operators are able to keep the dams closed up or at a slow pace during the day and let the water build up. And then in the evening, when we start getting close to a peak, they're able to open those dams up more fully, have more storage available, and run at max capacity for that time of day. A wind is not similar in the storage aspect, but if they have 1,000 windmills at their disposal, then they can run, as an example, 200 of them. And then when that peak time comes along, which is the high demand time of the day, they can bring on the other 800 and run them at max capacity. So that's how they're operating these windmills, and it's proven to be very effective. Solar jumps in there also. You can see today they've built a lot of solar over the last few years, and they're building a lot more still. But on a morning like today, there's only 7 megawatts of solar available, and they tend to work opposite each other. So a lot of solar is less wind, and a lot of wind is less solar. So a lot of times you get clouds, you have wind, and less solar. But if you look here, I'll bring your attention to the slide before that. Yesterday's solar portfolio on a partly cloudy day was 233 megawatts of energy being dumped into the system in real time of solar. So you can see it's not even 25% of what wind was doing on a low wind day. Does anybody have any questions about that? So that's how wind is intermittent, based on the environment conditions and based on the need of the grid. So I apologize. Any questions?
So to avoid confusion and get a clean recording, I think that we're going to carry on until the end of your presentation, and then I will stop and we can take questions at that time.
Okay, that sounds great. Thank you, Dana. So here they are compared side by side. Once again, 88-degree day, sunny with light clouds, and 2:30 is approaching the peak time of day. And when I say peak time of day, we're looking at anything from in maybe northern Michigan might be peaking. A city in northern Michigan might be reaching their max capacity due to an extremely hot day, a normally hot day for them, or maybe somewhere in Alabama is hitting a peak because it's extremely hot. Ours, the Midwest peaks based on the hottest day of the year and the coldest days of the year. So those are good examples of peaks. Now, like I said, we're comparing an 88-degree day that's sunny with a 74-degree day that's full cloud. Quite a difference. And one thing that didn't move much was your nuclear. Nuclear is kind of set in stone. There's not a whole lot they can do with that. Now, coal, you see a big difference in the coal here, and that's because they wouldn't have shut anything down to accomplish this, but they may have slowed it down. They may have choked it back a little bit to reduce its output. They'll be saving on resources and putting minimum nameplate capacity out rather than 100%. And I don't know what the percentages are, but that's the example I'm using. So this is also a real-time demand curve. Like we said, we're talking about demand of these sites. The wind was built to help with peak demand. Hydro is always a base load contributor that can also help address grid peaks. Coal plants, base load contributor, very minimal impact on peaks. But this right here shows us exactly what the actual load is at, this would have been at 2:40 yesterday afternoon. And it's quite high. So it's a lot going on. And they project this stuff days ahead of time, and they are typically pretty close. So this is a good comparison between your real-time generation and your day-ahead forecasting. They're quite a bit off here based on what I normally see, but they're still pretty close. You can see they've got the green line there, which is real-time generation, and then the day-ahead forecast is the blue. So the blue is telling us what they think they're going to use right now at the time this was taken. So they've got their peak correct, which is the AM peak, and then they're estimating that we're going to peak again here 6 p.m. or so, and then start dropping off for nighttime. So very interesting. And like I said, they typically forecast this out. This is a one-day snapshot ahead of time, but there are many people who are forecasting out even years ahead of time. So now, electrification, this is something I'm going to start throwing into the presentations that I do with wind, with solar, with hydro. What you're seeing is a decarbonization of the electric grid. So at one time, Indiana by itself was predominantly coal generation. So over the last several years, our industry has been investing in alternatives, which is some of these hydro dams were built many years ago, but the technology, take the Hoover Dam, for example, the technology for that turbine has changed so much that pulling out a generator, an old generator, and putting in a new generator becomes cost effective pretty quick. So that's what we're starting to see right now. We're getting a lot more energy out of the same amount of inputs. So the efficiencies are getting better. So wind, a lot of wind's been built, again, starting in 2003 here in our own state. expanding in 2008 in northern Indiana as well. It's just gotten very large. And solar, even residential solar, has grown tremendously in recent years, but industrial and commercial grade solar applications are becoming very normal. It's almost all electric distribution sites have an investment in one way or another in a physical asset of steel in the ground for solar. So not every electric distribution site has wind, but wind is definitely part of their portfolio. So they might be buying it from a site like that Orion group that built these, or Duke Energy's buying into that. Just a lot of investment in these alternatives right now. And it's because you can move them around. You can move them, you can turn more of them on during peak, you can slow them down during non-peak times, and you don't have to build a gas plant or a coal plant to accommodate your peak anymore. You can invest in a more viable and cleaner energy source, which is your solar and your wind and your hydro. So electric grid, a lot less carbon emissions as a whole. Now, this I thought was pretty neat. I started doing some research on some of the first wind. I went back to, this is a picture of the first windmill. So that generated, it was used to pump water for irrigation. So nope, I apologize. I'm telling you wrong. This one produced electricity. 1888, this windmill was producing electricity to the grid. It was built by Charles Brush, and some of the first windmills were built by the Persians in 700, somewhere between 700 and 900 AD, and they used them to pump water for irrigation. So this is a very unique unit, and it probably wasn't very high off the ground either. It looks like maybe 100 feet, 150 feet at the most. So it was in Cleveland, Ohio. So wind rotors are used for many applications. Again, grain production, potable water pumping, irrigation, industrial water supply, electricity generation. So over time, originally, the irrigation water, using windmills to pump water for irrigation, changed how people lived. Back in 700 to 900, you had to live around rivers where water was available all the time, and you could only grow so much agricultural products for food based on water in its location. But being able to pump it with a windmill, just simply putting a windmill and pumping it out to farther locations, societies were able to grow greater amounts of food for their populations. So it had a great impact on where our societies lived and how they lived as well. So the future of wind, so what we're starting to see right now is there's a lot of offshore opportunity. So there's struggles with that as well. But as these change, as the technologies change, the cost comes down and the output goes up. And it makes a lot of these options attainable. So the offshore wind opportunity, what would have been cost prohibitive a few years ago, is now starting to be an option. So these technologies are advancing and becoming more cost effective. And as they advance, the cost decreases, consequently increasing the economic value of offshore wind. So I think what we're going to see, maybe not in the next few years, but in the next 10 to 20 years, some of the articles I've read on this as I was putting this together, indicated that in the next 20 years, wind is going to really take the spotlight based on energy production. And a lot of that stuff's going to be offshore. And that can be your 30 meter to 50 meter sites, which are stationary. And then you've got floats. You've got units that float, the deep water systems. They'll sit out in the ocean and they'll be attached to the earth with cables. And they'll just sit out there and float and produce energy. And it seems like a futuristic way of doing this, but we're just about there. It's pretty neat. So some of the issues are deeper waters, which increases the cost to build, severe water conditions. I believe that's supposed to say weather. So we got some severe weather conditions, hurricanes, high winds, stuff like that make it difficult to work on. And the hurricanes are going to be sometimes catastrophic for these. Cable failures, cost reduction versus quality. So as the cost comes down, does quality suffer? Sometimes it does. So you start mass producing some of these things rather than like an on-demand production, there's a good chance you have less quality. So short-term thinking, what they mean by that is, are these units that float out in the ocean, are they going to be worth it or are they not going to be worth it? Short-term thinking would say, yeah, definitely they're worth it. And then retrospect, of course, gives you a full view of what the economic value of that investment would be. And sometimes you may not be able to squeeze the value out of it that was put into it.
So, Jeremy, I wanted to make the note that WebEx will kick us off in about 5 minutes.
Okay.
So just letting you know.
Well, let me just talk about this slide here. I want to show a national producer. So this is the Alta Wind Energy Center out in the Mojave Desert. And it is 4,731 turbines strong. It's got 3 different types located there. It covers 3,200 acres. And it produces 2,296 megawatts annually. And it cost $1.85 billion to acquire and build.